Um, okay, so first, exam 3 is a week from today. Whoops. No, you just got it back. Or no, you haven't gotten it back yet. You just got it scored.
Oh, okay, just check.
Okay. Someday, some of you will be teachers, asked to grade giant piles of things, and in your mind, you will apologize to me for all the mean things you're thinking every time I don't bring your stuff back. Okay, so exam 3. Yeah.
And I have a job in industry and no one meets that.
Oh yeah, I know, that's what, it's funny, I always think that whenever they're like, well, what are you going to do in industry when, yeah, teachers love to say that, and I'm always like, boy, no one ever seemed to care too much about deadlines at my job, but I usually just keep my mouth shut about it. Yeah, that is correct, that is what you're going to do. That's funny. Okay, so exam 3 is Tuesday the 28th. And the topics, remember all these are cumulative, although in statics that doesn't matter too much because everything just builds on the thing before. But all the topics up through structures. And if I give you a full structures problem to do, it takes up such a huge chunk of the exam period that I probably am going to break it up into different things. Like there'll, for example, probably be a complicated structure where I make you draw the free body diagrams. And then there'll be like a simple one where I ask for you to come up with the equations, but you don't have to solve them, like that kind of thing. So it probably won't be a structures problem all the way through, but it'll test pretty much all the different steps, with different problems. Anybody have any questions about the test? All right. Yeah. You haven't given it back yet. We're taking it next week and we still haven't gotten it back. That's you. Okay. So let me do a structures problem. I got a question about number 4. I think partly because there was possibly an error in the solution. I'm not sure. That doesn't sound like me. That's another thing. Getting all the solutions right is a surprisingly complex task. So this is structures number 4. And it looks like this. There is a straight bar, and it's connected to a semicircular shape like this. Ooh, that's a good semicircle. Don't patronize me. And then there's a pin down here. Okay, what do we know about and then the force is like this. This angle is 30 degrees. The length of the straight member is 0.4. And the diameter here is 0.6. And if I number it, like call that member 1 and that member 2, and I'll call the joints A, B, C. The mass of member 1 is 10 kilograms. The mass of number 2 is 50 kilograms. What are the internal loads? No, not internal. What are the external loads? That's the next topic we're going to cover is internal loads. The external loads on each member. So I'm going to do this both. Oh no, it has weight, so we can't do it as a truss. If we ignored the weights, we could do this calculation as a truss. It'd be sort of a cool. You know what? So this has it has a fairly big external force, bigger than either of the two weights. I'm going to do this calculation using our approach, and then I'm going to ignore the weights and do it as a truss calculation, and so you'll get another look at a truss simplification, and you'll also see how that approximation, how well it would work in a case like this. It's going to be great. Oh, I did say that. Well, I already talked about it again, so I might as well do the problem. So first, member 1, free body diagram of member 1. There is a pin joint at A, so I'll call that RA. There's a weight at the center. That's 10 times 9.81, so 98.1 newtons. And then at the joint B, what member is that pin associated with? 1 is the lowest numbered member. So there's a contact between the pin and 2. That's the force F12. Then there's the external force of 1,000 this way. And that's everything. So rho, force, moment. So for the about point, I guess I'll put it here, then F12 and the 1,000 will both produce 0 moment, and so it simplifies the moment equation a little bit. It's not a big deal either way, but so for F12, the rho vector is 0. The force is F12, x and y. The moment, 0. Same thing for the 1,000 Newton force. The rho vector is 0. The force is 1,000, 0. And no cross product. Then we have to figure out the rho vector at, I want to show you something cool. So first let's do the one at RA. So the rho vector is going to be the length of 0.4 times cosine and sine of 210 degrees. Can someone calculate that for me? 306? 46. Okay, and the force vector is R, A, X, R, A, Y. Cross product is negative 0.346 R, A, Y plus 0.2 R, A, X. Okay, the next thing I'm going to show you here. Yes. Yeah. This is 30 degrees.
No, the 210 is right.
Oh.
The numbers are
Oh, okay. What do you get?
I got cosine of 210 is negative 0.66, and sine of 210 is negative.
Yeah, times 0.4 though. Okay. Okay, no, that's great. It's so easy to make like little mistakes, so I appreciate it when everyone chimes in. So the last thing we have to figure out is the stuff for the weight. How are we going to figure out that? Well, we could calculate cosine and sine again, but I'm going to tell you something that's going to change your lives. I mean, really everything you encounter and everything you hear changes your lives, but this is going to change it for the better in a bigger way than some of that other stuff. And that thing is, if you want to calculate the midpoint between 2 points, how are you going to do that? Take the average. That always works. If you want to find the midpoint between 2 points, average the coordinates of the 2 points. Yeah, you'll use that a million times. Okay, so what that means is the row vector of this 98.1 is the average of 0 and this, so it's half of this. So 0.173 negative 0.1. Boom. The force vector is 0, negative 98.1. And what's negative 0.173 times negative 98.1? Okay. And so now Newton's second law says F12x F12y plus 1000 0 plus RAX RAY plus 0 negative 98.1 is equal to zeros. And the moment equation says, I'll just reorder those. So 0.2 RAX minus 0.346 RAY plus 16.97 is equal to 0. So we have three equations. The first one says F12x plus RAX is equal to negative 1000. The second one says F12y plus RAY is equal to positive 98.1. And the third equation says 0.2 RAX minus 0.346 RAY is equal to negative 16.97. And for variables, we have the vector F12 and the vector RA, and that's all. So we have 4 variables, 3 equations. Where do you think you're going? I'm not done with you. Okay, that's all right. Yeah, that totally makes sense. Okay, so now free body diagram of member 2. That's the semicircle. At C, there's a force vector from the pin joint, so that's RC. We got to calculate this centroid. Okay, well, so there's a weight at the centroid, and we have to figure out where that centroid is. So that's equal to 50 times 9.81, so 490.5. And then up here, that 1,000 Newton force is applied to the pin, which is member 1. So this only has the force on 2 by 1, or negative F12. Well, you could look up that centroid, or you could do the integral. Which one are we going to do right now? Okay. Anybody remember? Do you have the formula in front of you or anything? It gives a okay. Oh, I gave it to you. That's great. Okay, so okay, and that is from this side. It looks like. So this distance here is 2r over pi. It's not the 4r over 3 pi one, because that's a solid circular thing. This is a arc.
Could you just do the bigger of the two part minus the smaller of the two? That works.
Oh yeah, if you did them as solids.
Yes. That's a good way to do it if you know the thickness.
Sure.
I suppose if you don't know that formula assumes that thickness is 0, you know, but that's like the limit so that's a better way an easier way to do it than the integrate. Do the outer, subtract the inner, do the subtraction formula for the inner, and then you could look at how the formula would limit as the difference between those radii went to 0. What? That was the one that's posted on D2L, right, Scott? Okay, yeah, it's on D2L. Yeah, that's true. I like it more when you insult other people. Yeah. I always find that pretty funny, but I didn't find it so funny this time. So this is everything. So rho, force, moment. And I'll choose the about point down here at C. So for the force RC, the rho vector is 0, 0. The force is RCX, RCY. No moment. And then at the top, the rho vector is 0, positive 0.6, because that's the diameter. Force vector is negative F12X, negative F12Y. And the cross product is positive 0.6 F12X. And then for the weight, the rho vector is, well, we know the y component is 0.3. The x component is 2r over pi. R is 0.3. So what's 0.6 over pi? 191? 0.191. And the force vector is 0, negative 490.5. And then what's 0.191 times 490.5? 93.68. So Newton's second law says RCX RCY plus negative F12X negative F12Y plus 0, negative 490.5 is zeros. Rotational equation says 0.6 F12x minus 93.68 is 0. So equation 4 says RCX minus F12x equals 0. Equation 5 says RCY minus F12y is equal to 490.5. And equation 6 says 0.6 F12x is equal to 93.68. And the variables, so before we had F12 vector, RA vector, and now we added RC. So we have 6 equations, 6 variables. All right, well, let's write out the matrix for this. So it has to have 6 rows and 7 columns. The rows are the equations. And the columns, let's do it. F12x, F12y, RAX, RAY, RCX, CY, and then the constants. Could someone, just so I don't have to keep scrolling back and forth, could someone read me what the coefficients are for these?
First line is 1 for F12x.
Okay.
1 for RAX.
Okay.
And then
Okay.
2 is 1 for F12y.
Okay.
1 for RAY.
Mm-hmm.
And 98.1. 3 is 0.2 RAX. Negative 0.346 for RAY. And 16.97. Negative 6.
Okay. All right.
And 4 is 1 for RCX. And negative 1 for F12x.
And 0? Okay.
And 5 is 1 for RCY. And negative 1 for F12y.
And
490.
okay.
And 6 is 0.6 for F12x. And 93.68.
Okay. Could a few of you, a couple of you, take a second and calculate those values? Okay. Yeah, whoever's watching this won't see any of that. So let's do the external loads. So on this one, we have RA. So down here we have a force of negative 1156.2, negative 619.26. And up here we have F12 plus that 1,000 Newton force going to the right. So this is positive 1156.2, 717.4. And then acting down is the weight, what was that, 98.1. And then the semicircle Down at the bottom has RC. That's 156.17, 1207.8. And then the weight acting at the centroid is 490.5. And then up at the top, negative F12, so negative 156.17, 717.4. Yes. Are we really going to do this as a truss? I think not. Anybody have any other questions? Other problems you'd like to do? Yeah. You can't add, the only things you can add are things that happen at the same points. Okay, so that weight is acting at the centroid, and you can't add that to anything. The ones up here you can add together because they're happening at the same point. Okay. There is one thing that's sort of interesting about this, like if you were going to do this as a truss problem. So what if you had a truss? So you had this connected by a pin joint to the semicircle. And then the 1,000 Newton force here. If you ignore the weights, you can think of this as a truss. Yeah, I'm going to do this because this happens to be a really fast one. The question with this is, what direction is the, when we isolate this pin up here, what direction do we treat the force applied to that pin from this curved member? We've only dealt with straight members before with trusses. So I think this is a good little reminder about like what direction those forces go in a two-force member. Okay, so let's call this member 1 and member 2, A, B, C. And for the truss simplification, I'll isolate pin B. Well, what's acting on B? There's the 1,000 Newton force to the right. And then we're going to assume that member 1 is in tension, so I'll call this force F1. That's member 1 pulling on it. And then what do we know about the forces applied to member 2? They have to be equal and opposite, and they have to be parallel to some line. What line? Between the two joints, that's right. So usually you think of that line as being along the member, but if the member is curved like this, you have to remember that it's parallel to the line between those two joints. And so the force applied by member 2 would just be straight down. So Newton's second law says that would be negative 0.866 F1, negative 0.5 F1, plus 1,000 0, plus 0 negative F2 is equal to zeros. So F1 is, so what's 1,000 divided by 0.866? Just, what is it? Okay, 1154. Okay, and then plug that into the second equation. What do you get for F2? So negative 0.5 times 1154. Okay, and that's negative. So what we get in this case is that this member is in tension with a magnitude of 1154. And this member is in, you really wouldn't call that tension and compression anymore, but it's, these forces are pushing towards each other. Magnitude of 577. And well, when we talk about internal loads, we'll talk about what I think of as compression, which is a point-by-point analysis of what's going on inside the body. And in this case, there'd be this weird stuff going on, like if you try to bend it here, for example, so I wouldn't call that compression, but there might be some area where you would. And you can see that it definitely doesn't match the results we got before, but not by a long shot on the curved member, I guess, but on this one it's a little closer. Okay, no more questions about structures? All right, let's start talking about internal loads. So the next topic, this one is not going to be on the exam. So not on exam 3. But the motivation for internal loads calculations is basically this. I feel like I've drawn this picture a lot this semester. I've probably already drawn this in this class, but okay, that's supposed to be a hand. Here's the other hand. So say you're bending the stick. If you think of a free body diagram of the stick, it looks something like this. What? I think so too. I bet that would be a really popular display or whatever they call it. Yeah, right. We should actually, yeah, we should. Like, what about the art gallery and the Normandale Art Gallery? That'd be really funny. Like, yeah, huh, yeah. I'll talk to them about that. I like that idea. Engineering drawings. Yeah, yeah, right. Yeah, exactly. Um, but if you did a free body diagram of the whole stick, the thumbs would be pushing up. The fingers will treat them like they're all doing the same thing. You could imagine doing this with just like a finger, and um, it'd be symmetrical. So you'd have this. And so that's a pretty complete description of all the external loads. But you know from experience that this stick, when it breaks, is not going to break at any of those four spots. You know, so why won't the stick break at those four spots? You know, this sort of gets at like how useful are these external loads for helping us predict where something is going to be damaged or whatever. You know, from experience, you know that it's actually going to break in between the two thumbs somewhere, right? So is there any way, the question is there any way for us to do a calculation that will predict that it's going to break between those two things? One of the main questions in mechanics is the thing going to break, and correspondingly, like where, you know? So is there better calculation for predicting failure? And the answer is internal loads. And so the idea of internal loads is if this is the stick, we're not going to isolate the whole thing. We're going to just isolate part of it, okay? So this black part is our chosen body. And there's a force F here, a force F here. These forces F that now are not part of our free body diagram, okay? And so now think about this, this little piece of the stick that I chose to isolate. Is that a complete free body diagram of that piece of the stick? Well, like we're ignoring the weight, I guess, but you just go around the boundary looking for contact. Is there any place else where the outside world makes contact with our chosen object? Gravity, but there's something going on besides that. Yeah, the right at this boundary here, which we chose that to be the boundary, but right at this point, there's a fixed joint between this and this, And so, since this is a fixed joint, what kind of loads are being applied to the black part by the blue part? You're naturally good at this. She's taking another class where we've been talking about this for 3 weeks. I gave away the secret. We were going to do a thing where, like, she would just keep answering every single question, you know? Okay, so this is, so there's a reaction force like that, and a reaction couple like that. I'll call it MR, reaction moment. And we know that it's a full force vector and a moment like that, a couple like that, because that's what a fixed joint does. You know, this is like a weld joint between those two halves. And these loads then are the internal loads. And these internal loads, like where those are big, that's where the thing breaks. Well, that would be an easy way to represent it. We don't do it that way. I mean, the idea is this, but we don't use that notation because, you know, there's sort of one more little wrinkle. We don't use the vector sign convention because it would lead to opposite signs in your internal loads depending on which half you isolated. Half. Okay, so think of what would happen here. So there's the black part and the blue part. So say that this is how we calculated internal loads. Okay? That is the idea of the internal loads right at this point. Okay, and we want a set of internal loads that describe the the magnitude of the deformation at that line. Okay, at that interface between the black part and the blue part. Okay, we just want one set of values. Well, if you isolate the black part, you get these. Okay, but what do you get if you isolate the blue part instead? I mean, that's, and still use the same idea to calculate this line. Yeah, because it's a Newton's third law thing. You know, the force on the black by the blue is this, then the force on the blue by the black is negative R and negative MR. Okay, and so that indeterminacy makes us want to come up with one sign convention that's going to give us the same values for a chosen interface, no matter how we calculate it. Okay. Well, the signs mean something though too. So we don't want to throw away all the directional information, but we need a way that it's consistent depending on which way we're looking at it. Yep. Yes. Yeah, that can be a little bit. I mean, that is something that's going to be an issue. Like that's a good thing to think about. Well, if we knew how much of it, if we knew how much of what percentage of that stick we were isolating, then we'd say this is a third of the stick. Then we know a third of the weight is here, and that third of the weight isn't going to act at the center of mass of the whole thing anymore. It's going to act at the center of mass of the piece we're isolating. And so, yeah, that is going to be an issue, you know. So here's the sign convention we're going to use. On this side, if we have, you can think of it as if we have material on the left and space on the right in our isolated piece. The horizontal force is going to be represented by T. The vertical force is going to be down and represented by V. And the bending moment, M, is like that. T equals tension. If you get a negative value, that's compression. V is called the shear force. And M is called the bending moment. And if you have the opposite situation, where you have material on the right and space on the left, then the sign convention is T going this way, V going this way, and the bending moment this direction. So since, depending on how you cut the piece, you switch the direction of those internal loads. Now what we get is, no matter how we calculated those internal loads, we get the same values. So you can say that those three values, T, V, and M, actually just uniquely represent what's going on at that boundary. Okay, that's the idea, and it's not something you have to like understand. You know, it's not a real big deal that you understand it carefully, but if you ever ask yourself, like, it's useful to remind yourself that all we're doing is calculating the reactions at a fixed point. And if you think about it that way, you think like, well, why did we have to change the sign convention to these new variables? And the reason is just because of this indeterminacy, you know. Okay, so let's do our first calculation. Let's say that there's a beam with a 500 Newton force down on each end and a 1,000 Newton force up. The whole thing is 1 meter. Let's say that 1,000 is at the midpoint. And let's calculate the internal loads here at A. That's a quarter of a meter from the left end. Okay, so what we're going to do is draw a free body diagram of that left piece. And that means we're excluding all this. The piece we're excluding has a force up there, a force down there, but those aren't happening on our chosen piece. On our chosen piece, we have a downward force of 500 here. And then we have a fixed joint at the boundary between the two pieces. And I'm going to represent that as tension, shear force, bending moment. This distance is 0.25. So now how do we calculate T, V, and M? Yeah, I mean, we're just going to use Newton's laws. So we use Newton's second law and the rotational equation. That's 3 equations for these 3 variables. Okay, so that's always going to be the idea. Newton's second law says 0, negative 500 plus, I think the best way to think of this can get confusing with the V sometimes. And V is always pointing down. Think of the arrow with the variable as a number multiplied by a unit vector. The arrow is a unit vector. So what's a unit vector in the direction of T there? 1, 0. So if you multiply T times the unit vector 1, 0, you get the vector T, 0. And then V times the unit vector down. What's a unit vector down? 0, negative 1 times V gives you 0, negative V. Add those up, you get 0. So you can calculate those, and you get, in this case, T is equal to 0, V is equal to negative 500. And now we have to calculate that bending moment. We'll do that with the rotational equation. Okay, so this is just how we're always going to do it. Makes the calculation a little easier. We'll always choose our about point to be at the left-hand point. And then we're going to calculate the moments produced by each of these loads. You could write this out as rho force moment and calculate it that way. Since these are all horizontal, you'll find in the long run it's faster to just sort of think through it. So what's the moment about the red dot produced by the 500 Newton force? 0, yep. What's the moment about the red dot produced by T? 0. What's the moment produced by M? M is just a couple, so that's plus M. And now, what about V? Yep, you can think of, there's a moment arm of 0.25 times V, and if you apply the downward force here to a thing that rotated around this red dot, it would make it rotate clockwise, so that's negative. So minus Vx, V times 0.25 is equal to 0. And so M is equal to 0.25 V. We already calculated V, so plug that in and you get M is equal to negative 125. This is newtons, this is Newton meters. Any questions about that? Yes. Yeah. Yeah. So if you're trying to find the bending moment at a different point, over here, here. Yes. Okay. Is there a way to? Oh, could you just say? I see. Could you just say 0.25 times 500 and skip all the other stuff? In this case, you're right. In the general case, the way that I showed you how to do it here is going to be the fastest way. And it's nice because you just always do it the same way, so you won't make as many mistakes, you know. So get in the habit of doing it this way, you'll be happy in the long run. But yeah, you're exactly right. Okay, well, is that the same internal loads that you have at every point along the beam? No, it would be different if you chose different points. You know, like if we chose 0.1 meters from the left, you'd get different values. And normally what you want to do is you want to find how those internal loads vary as you go from one end to the other. We'd like to know the internal loads everywhere along the beam. We've calculated one so far. You know, we have uncountably, infinitely many more to go. So that seems like a long process, you know. So we could just roll up our sleeves and get to work, but what we would like to do is come up with a way to represent these internal loads as a function of x, you know. So we want these functions t of x, v of x, and m of x. That's what we're looking for. So now let's do a similar example. And, well, it's the same beam. This time, how do we want to do this? Let's choose a length of beam x, where x is between 0 and 0.5. Okay, so let's think of what this represents. We want to come up with a free body diagram that's a general representation of all of these pieces of beams where the right end falls somewhere between 0 and 0.5. So we want to represent, here are all the cases we want it to represent. Just a little tiny piece where we're ignoring all that. And we also want it to represent some intermediate case where we have a little more beam that we're isolating, but we're still ignoring the force up in the middle. We're still ignoring this. We have the 500, and we have T, V, and M. And we also want it to represent the case where we almost get all the way to that middle force, but not quite. So we still aren't including that upward force. We're still not including that force. And we still have 500 T, V, and M. And looking at these three things, you start to see a pattern. There are some features that all of these free body diagrams have in common. You know, even though the lengths are different, all of them have this 500, and they all have those three internal loads and nothing else. You know, so we'll represent this generally. We'll represent it by the general free body diagram. We're ignoring all this stuff. Where we have the 500 Newton force down, the internal loads, and this distance here is x. And now we're going to use Newton's laws exactly the same way as we did in the specific case. Newton's second law says 0, negative 500 plus T0 plus 0, negative V is equal to zeros. And that tells us that no matter what x is in that range from 0 to 0.5, T is equal to 0, and V is equal to negative 500. And then the rotational equation, we'll choose this as the about point again. What's the moment produced by the 500 Newton force? 0 by T, 0 plus M minus, well, so let's think about this moment now produced by V. It has a moment arm, before it had a moment arm of 0.25. Now we don't have a number for it, we're just representing that moment arm by x. But we have a moment arm of x times the force of V, and that force V would make it rotate clockwise. So that's a minus Vx. Is equal to 0. And so M is equal to Vx. So plug in the value for V and you get that M is equal to negative 500x. And so that says for any x value between 0 and 0.5, these functions represent the internal loads. Okay, so if we had gone, like, what's another approach to calculating the internal loads everywhere besides coming up with these functions? Well, one approach is just to do, think of it as like a numerical approach. You could just do this analysis at 10 different 10 different lengths, 10 different points, and then just interpolate between those points or whatever to give you a sense of what the internal loads are. But with that general approach we did, say you did 10 different values of these, the calculations that you did in those 10 different cases would match what you get for plugging those values in for X. That's the benefit of this. Any questions about that? All right, so the last question I have is, why did I choose X to be between 0 and 0.5? Why not do the whole beam? Yeah, so why don't these functions hold for X greater than 0.5? And the answer is, do a free body diagram for X equals 0.75, just as an example. What you get is this new thing, where this distance is 0.75. And now, because there's that 1,000 Newton force, our general free body diagram that we did doesn't represent this anymore. You know what I mean? The features that these three cases all had in common, this new example does not have in common with them. Okay? And so we can, so if we want to calculate what the internal loads are for X values between 0.5 and 1, we need a new free body diagram, a new general free body diagram that incorporates this 1,000 newtons. Okay, so we'll just keep going with that next time. Anyone have any questions about this? The kind of idea here makes some sense, hopefully. But when you get confused about this stuff, just remind yourself that the calculation we did with the general, in that general case, this calculation was exactly like that simple calculation we made where the length was 0.25. The only change was that now that distance was called a variable X. All the calculations followed the same approach.